Good morning, everyone, and welcome to our Bussmann University webcast series. Today is part one of a two-part session that will cover how to calculate the short circuit current rating, or SCCR, of an industrial control panel using UL 508A supplement SB. We have previously covered proper application of SCCR and NEC requirements, which you can watch on demand in the Bussmann University portal. My name is Joe Shoemaker. I'm Manager of Technical Sales with the Bussmann team, and I'll be your moderator for today's webcast. Throughout the webcast, you're welcome to submit questions in the Q&A portal, and we will do our best to answer all questions during the webcast. After this live broadcast, you will receive a link to watch this and all the previous Bussmann University webcasts on demand. I'd like to introduce Christy McElhinny, Field Application Engineer for Eaton's Bussmann Series solution. Christy provides technical guidance to consulting engineers, OEMs, electrical contractors, and industrial and electrical inspectors in her territory covering the Northeast United States. She is sought after for her expertise on overcurrent protection. I'll now turn it over to Christy.
Thanks, Joe. Good morning, everyone. I am going to go ahead and dive right in because we have a lot to cover here today. So our agenda for today, we're going to start with some key terms and definitions. UL 508A sort of has its own language, and it's really important we understand that language before we can really understand how to determine the panel short circuit current rating, and then we'll get into that. We'll get into those steps, and then we'll do some example and practice problems. We'll do one today, hopefully, and then a lot more in our part two of this presentation. So the first, probably most important definition that we have is what is short circuit current rating. So short circuit current rating is defined as the prospective symmetrical fault current at a nominal voltage, which an apparatus or system can be connected to without sustaining damage exceeding defined acceptable criteria. And that last part's actually very important, right? Without sustaining damage exceeding defined acceptable criteria, which of course implies that there can be a little bit of damage. So short circuit current rating doesn't necessarily mean you're going to be able to use it again after a short or a fault. It just means that you haven't created a hazard or an excessive amount of damage after it. The hazards of insufficient SCCR, that's a shock, fire, or a projectile hazard. So if we avoid those and avoid excessive damage, then we have a short circuit current rating for my equipment. The next important definition is the definition of an industrial control panel, right? That's what we're trying to determine the short circuit current rating of. The NEC defines an industrial control panel as an assembly of two or more components consisting of power components only, control components only, or a combination of power and control circuits. That's what number three is what we typically think of as an industrial control panel, that combination of the two, but power, control, and or a combination of the both. Very importantly, the industrial control panel does not include the controlled equipment, right? So whatever it is feeding, motors, lights, whatever it might be going to, that's not considered part of the panel. It's only what is inside that probably gray box that counts towards it. So it's also very important that we define power circuit versus control circuit, right, since that's what makes up my industrial control panel. A power circuit, those are my conductors and my components of branch and feeder circuits. Now, of course, we don't define branch and feeder circuits till the next slide, but the easiest way to know if something is a power circuit is if it is between your supply and a load, right? So if it feeds an external load, that makes it part of the power circuit. A control circuit, right, that's electrical signals, right? Inputs and outputs, it's usually very few amps, right? I mean, 15 amps at the most. It could be more, but in most cases, it's very, very few amps. In many cases, it's a different voltage, so it doesn't have to be. You will note that voltage is not mentioned here, right? I know it's really easy for a lot of us to think, oh, the power circuit, that's our 480 volt part. Control circuit, that's my 120 volt or 24 volt DC. But that's not necessarily the case. You can have power circuits at those lower voltages, right? As it goes to an external load, that's a power. I could have a 120 volt motor or a receptacle on the outside of my panel that anybody could walk up to and plug something in. That makes it an external load. So if it goes to an external load, it's part of the power circuit regardless of the voltage, right? It's all about whether or not it feeds a load. You'll see this little sticky note on the side of this slide here, important to note, right? Why we care about power circuit versus control circuit, it's because the SCCR applies only to my power circuit. We get to ignore control circuit devices. There are a couple other components that simply do not have short circuit current ratings. The ones we run into the most is number one there, that transformers, reactors, CTs, capacitors, resistors, varistors, voltmeters. We also see number 5 a lot, that EMI, RFI line filters. Those do not have an SCCR, so we get to, again, just ignore them. Even if they're in our power circuit, we get to ignore them when we're calculating short circuit current rating. Next, we're going to go ahead and dive into the definitions of a branch circuit versus a feeder circuit, right? So I told you my power circuit was made up of branch and feeder circuits, so I should define exactly what those are. My branch circuit, those are my conductors and components following the last overcurrent protective device protecting a load, right? So if I'm looking at my one-line diagram and I look at my load, I just go up, up, up until I hit an overcurrent protective device. And by overcurrent protective device, generally that's a breaker or a fuse. But when an industrial control panel, sometimes it's something like a manual motor protector, right? It's where that short circuit protection is in my circuit. So I go up until I hit that, and everything that's in between it, that's all part of my branch circuit. My feeder circuit is anything that supplies a branch circuit. So if it's on the supply side of my branch circuit, that's part of the feeder circuit. So in this sample panel we've got shown here, you can see my branch circuits, right, last overcurrent protective devices before my load. So it looks like I've got fuse breakers and contactors below those. Those are branches. And feeding those is a fusible switch and a power distribution block, right, on the supply side of my branches. Therefore, they're in my feeder circuit. And the last really important definitions that we understand are the difference between a power transformer and a control transformer. I'm going to actually start with control transformer is a transformer whose secondary supplies power to control circuits only. Right? So if every single thing on the secondary of my transformer goes to control, it is a control transformer, and therefore all of those secondary devices get to be ignored when I am calculating short circuit current rating. A power transformer is a transformer whose secondary goes to a branch, right? Any sort of load, if it goes to a load, or a combination of loads and control devices, right? This makes sense. If I've got a 120 volt load and 120 volt control power, I'm not going to have two separate transformers, one for the control and one for that receptacle. I've got one transformer, and it, you branch off and you feed the load and you feed the control. But as long as it goes to one load, it's considered a power transformer. So power transformers we do consider in short circuit current rating. They are still part of my power circuit. So we do consider the secondary devices that supply loads. I still get to ignore the control circuits, but if it supplies a load, those part of the secondary of my power transformer, those I include in my calculations. So we've got a nice example panel here to show you, right? So I can see I've got a main circuit breaker. It looks like I've got a power distribution block after it. And then I've got, you can see two branches where I've got, it looks like a combination motor controller, right? A motor circuit protector and a contactor. And then one where I've got circuit breaker feeding a soft start. And then you can see all the way in the top right hand, I've got fuses feeding a control power transformer, right? So my branches are that last overcurrent protective device before my load. So those are my motor circuit protectors and my circuit breakers in this case, and then everything downstream from it, that's all going to be part of my branch circuits. Those on the supply side, so in my feeder circuit, circuit breaker, and that power distribution block, those are going to be a feeder. It's also really important to note, so the SCCR, it applies to my branch circuit, applies to my feeder circuit. It also applies to the primary protective device go into my control circuit. So in this example, we have a control power transformer, but it could be a power supply as well. So whatever the primary protection for that device is, that still counts towards my short circuit current rating. Once I go through it, once I go through the power supply or through the control power transformer, if it truly feeds control only, then that can be ignored. But again, that primary protection still counts. So with that, we have reviewed all of the really important definitions, and we're going to go ahead and dive into how we actually calculate the short circuit current rating for an industrial control panel. And most importantly, we know that the panel short circuit current rating is going to be based on the ratings of internal components. There's two ratings that we're going to care about: short circuit current ratings and interrupting ratings. So I'm going to talk about interrupting ratings here first real quick. So an interrupting rating applies to an overcurrent protective device. And again, that's the device that's going to interrupt the fault, right? A breaker is going to trip, a fuse is going to open, maybe a manual motor protector, that's going to trip. So it's the device that's physically interrupting the fault. And these have interrupting ratings, right? And it's 35 KA, 65 KA, whatever it might be, has an interrupting rating on. That's one of the ratings we care about. Really important thing to know about interrupting rating is that no matter what, interrupting ratings can't be changed. So, you know, if the interrupting rating is considered the maximum amount of current that this device can safely interrupt, right? And that amount doesn't change based on what's in front of it or what's below it, right? It's just the amount that it can do. So interrupting ratings cannot change. They cannot be raised using current limiting devices in front of it. The interrupting rating is the interrupting rating. Short circuit current ratings, on the other hand, can't. So these apply to basically all of the other devices, right? The devices where when they see a short circuit, they don't do anything. They sit there and they wait for an upstream overcurrent protective device to open and protect them, right? So you think about a power distribution block, think about a contactor, think about a non-fused switch, right? Whenever there's a short, they don't do anything. They sit there and they're waiting for another device to open and protect them. So short circuit current ratings can change depending on what the upstream overcurrent protective device is, right? So they might have a short circuit current rating with a breaker that's different than with a fuse. So short circuit current ratings can change depending on upstream devices. Interrupting ratings cannot. Talking a little bit more about short circuit current ratings. So any component that is UL listed is going to be tested with an upstream overcurrent protective device to obtain a short circuit current rating. And so when you look up that short circuit current rating, you will see that component short circuit current rating value, so what it is, 5 KA, 10 KA, whatever it might be. You will see that upstream overcurrent protective device type and size listed. And that size, that is a maximum amp rating. So you are always allowed to use a lower amp rated device, but you can never use something higher. So it's a maximum size of the upstream device. There may be other conditions listed. Typically that's going to be something like conductor sizes that you have to use. And then you may see more than one short circuit current rating listed on a product, and we'll actually go through what all of the different types of component short circuit current ratings are that you might run into. So there's 4 types of short circuit current ratings for any electrical component. There's a standard fault, a high fault, group motor, or a combination motor controller rating. So let's first talk about a standard fault. The standard fault rating, this is the minimum rating that any component must have when it's tested with an overcurrent protective device. So you could kind of consider this like the default rating for anything. These are generally pretty low. If you look at UL table 508A UL 508A table SB 4.1, you can see all of the default ratings for different types of components in here. So they're not very high, right? We see a lot of 5 KA, 10 KA, some of them are even 2 KA, so they can be pretty low. You are always permitted to use this short circuit current rating. Generally, we are hoping to use something higher when we're trying to get a higher short circuit current rating out of our equipment, right? But this is basically, if you're not taking advantage of any of the other higher ratings available, this is what you wind up with, is this default rating, this standard default rating. You can always find that rating, should be listed on the product, but you can also find it in table SB 4.1. The next type of rating is a high fault rating. So this is a higher rating, optionally higher, right? And it's going to specify that maximum amp rating of that overcurrent protective device, right? So when I look at this contactor here, I can see the basic rating is listed in SCCR. It's 5 kA with a 45 amp fuse, or 5 kA with a 35 amp circuit breaker, or a high fault rating, right? 480 volt high fault. It's 100 K with a 20 amp Class J fuse. And what's interesting here is now it's actually specifying Class J. The basic rating didn't specify, right? It's going to assume any branch rated fuse there, but now for the high fault rating, it might get specific on the class of fuse. It is not, however, part number specific, right? You don't look at this high fault rating, it doesn't tell you got to use Bussmann LPJ-20SP, right? It just says any 20 amp Class J fuse. So it's sort of a generic combination rating in that way. And then of course on this one you can see there's a separate high fault rating at a different voltage. The next type of rating is a group motor rating. So group motor is when you have one overcurrent protective device that feeds multiple motor controllers that each have their own overload protection, and those each feed a motor load. So these are pretty similar to a high fault rating, but because that upstream overcurrent protective device is larger, right, you're going to use a larger, in this case, fuse, if you're feeding 4 controllers that each go to a motor, as opposed to if you had 1 fuse per controller. There are reasons you may want to do this in your equipment. There are reasons you may want to avoid this in your equipment. It is permitted per UL 508A as long as you're following all of your overload and top roll reasons, and there's a separate group motor rating. So just when you look up that product and you find the table specifically for group motor installation, and then that's the value you have to use. So just important that that's what you're looking at when you're using a group motor installation. The final type of component short circuit current rating is a combination motor controller rating. So a combination motor controller rating is a specific combination of components. So now, unlike a high fault rating, which was sort of generic, right? Any Class J fuse, this is a specific part number, so part number specific. It is for branch circuit use only, so you'll never see a combination motor controller in a feeder. It will only be in your branch, and it feeds a single motor load. So that is what's going to make a combination motor controller. The combination short circuit current rating applies to the entire combination of components. So, if I have part number A plus part number B plus part number C, I say those 3 all together have a combination rating of 65 kA, let's say, right? So you don't have to separately list each one. It's that combination has one short circuit current rating. And again, this one's just very important in that it is part number specific. Okay, so now that we know all of the ratings, right, that's important we understand both that short circuit current rating and interrupting rating. Now we can take those and we can apply them to determine my overall panel short circuit current rating. So the steps to determine it per UL 508A SB 4.4, and my step 1 is to determine the short circuit current rating of each branch circuit. Step 2 is to determine the short circuit current rating for each feeder component. Step 3, identify the interrupting rating for each overcurrent protective device. And then step 4, everyone's favorite step, pick the lowest value from step 1 through 3, and that is your panel short circuit current rating. So we're going to spend probably the most time today on part 1, step 1, because step 1 is the most complicated step. Step 1 actually has a part A and B here. So we're determining the short circuit current rating of each branch circuit. So we start by identifying the short circuit current ratings of each branch circuit device. That's the difficult part here is actually looking up all of these ratings, so it's time consuming. And then there's this part B where we can determine if my branch component short circuit current rating can be raised using feeder components, right? So that's kind of a weird one. We'll spend a lot of time on how exactly that works. But let's start right with that part A. So identifying the short circuit current ratings, right? So if I'm going to identify what short circuit current ratings can I use in my branch, well, I can use the short circuit current rating that's marked on the component or in the instructions that's provided with it. I am always permitted to use that default rating, that standard rating from table SB 4.1. Or, of course, if I have a component where I have a high fault rating with it, I can use that assuming I am applying the proper overcurrent protector device in front of it, right? So if it says that I have a high fault rating with a 20 amp class J fuse and I use a 20 amp class J fuse, I can go ahead and use that high fault rating. So those are the ratings, of course, that I can use in there. There are 4 sort of exceptions here, right? So in a high fault rating, remember how I said it's sort of a generic rating, right? It just says any 20 amp class J fuse. I'm actually permitted per this exception, exception 1, that if I have a high fault rating listed with a specific fuse, I can use a fuse that has equal or less than peak let-through current, which is essentially saying it's more current limiting. If I can use a more current limiting or equally current limiting fuse instead of that fuse, and I can still use that high fault rating. Right, so there's 2 main reasons we see this. So one is if you know the Bussmann cube fuse. The Bussmann cube fuse is equivalent to the class J fuse for peak let-through current. So if a component is listed with a class J fuse, I am permitted to substitute the class CF, that cube fuse, for it instead. There's reasons the cube fuse is usually smaller and touch safe, and reasons you might want to use that instead of the class J. But a lot of components are only listed with class J, but this permits you to use a cube fuse instead. It would also permit you to use something like a class CC fuse instead. Something, again, smaller, less expensive. It only goes up to 30 amps, but if something's listed with a 20 amp class J and you want to use 20 amp class CC, you can do that per this exception. So equal or less than peak let-through current. There's another exception here. So this actually has to do, and we'll see an example of what this looks like, but if the protection is provided in the field, so basically if you're being fed from something like a safety switch in front of the panel device, you can, with a specific marking requirement, you can still use that. So we'll see an example of how all of this works later, so I won't spend too much time on it now. Exception number 3 is just like exception number 1, except it has to do with circuit breakers, right? So I can use a listed current limiting breaker that is equal or less than peak let-through value, substitute it for the specified breaker, provided that the specified breaker is current limiting. So basically, if I have 2 current limiting breakers, I can substitute an equal or less than breaker for it as well. Very, very similar to number 1. Except with current limiting circuit breakers. And then the final exception, right, the final substitution I'm allowed to make is a current limiting fuse can be substituted for a non-current limiting overcurrent protective device. Now, this is usually going to be something that's listed with a breaker, but in this scenario would then not be listed with a fuse. Usually they're listed with both, but if for some reason you run into one and it's listed with a breaker but not a fuse, you could substitute that fuse and still use the high fault rating that it had with the breaker. That's what this exception allows you to do. All right, so with that, that's step 1A, right? Determining all of my short circuit current ratings in my branch circuit. 1B, right? Determine if this branch component short circuit current rating can be raised using feeder components. So what does this mean? What feeder component can I use to raise the short circuit current rating? I can use a power transformer, I can use a current limiting circuit breaker, or I could use a current limiting fuse. 4 here is a current limiting breaker or fuse supplied in the field with the marking requirement. We'll look at that again more in detail later. But let's start with this power transformer example, right? So if I use a power transformer in my feeder, right? So again, this is not in my branch, this is in my feeder. So if I have a circuit supplied by the power transformer, I can look up the short circuit current let through of that transformer. So if I have a single phase transformer, I look at table SB 4.3. If I have a three-phase transformer, I look at table SB 4.4, and in there it will tell me what the secondary short circuit current is on that transformer. And then what I can do is I can take that secondary short circuit current rating and I compare it to the downstream ratings, right? Interrupting ratings and short circuit current ratings. And if that secondary short circuit current, if it is less than all of the ratings of the downstream components, then what I'm permitted to do is say that the short circuit current rating of that entire branch is equivalent to the primary protective device interrupting rating from that transformer. So let's do an example because it's a lot of words and it gets kind of complicated. So in this example, right, I have a single phase 3 kVA transformer with 120 volt secondary. Downstream from it, I can see I have a component that has a 5 kA rating, and I've got this breaker that has a 10 kA rating, right? And what I'm going to do is I'm going to go to table SB 4.3, because again, that's for single phase transformers. I'm going to find my 3 kVA transformer, 120 volt secondary, and it'll tell me the secondary available short circuit. So the secondary available short circuit in this case is 1200 amps, or 1.2 kA. So I take that 1.2 kA and I compare it to 10 kA and 5 kA, and last time I checked, 1.2 was less than both 10 and 5. So as a result, I get to make the short circuit current rating of this whole branch equivalent to the primary overcurrent protective device interrupting rating of that power transformer. In this case, I'm using a fuse. It has an interrupting rating of 200 kA, so I have a 200 kA circuit here. Very important to note, right? I don't just get to automatically make it 200 kA. I make it whatever the interrupting rating of that primary protective device is. So if I'm protecting this transformer with a 10 kA breaker, it's all 10 kA, right? It's not an automatic 200. It becomes the primary protection interrupting rating. So this is why in many cases, when I have to consider the short circuit current rating of any loads off of a transformer, right? As long as it's going to an external load, I need to calculate it during my short circuit current rating, but it's usually not a problem because I'm allowed to use this. I'm allowed to calculate that short circuit current through the transformer. It's pretty low in most instances, lower than the ratings of any downstream components. So just because it usually turns out okay, we still have to know this step and do this step every time we have a load at that other voltage. Next, we're allowed to use, right, so we were allowed to use a power transformer. We're also allowed to use a current limiting circuit breaker in this feeder. And something that is just really weird and quirky but important to know about current limiting circuit breakers is that a current limiting circuit breaker does not count as current limiting unless it is marked current limiting. So every circuit breaker technically is a little bit current limiting, but unless it is marked current limiting, we don't get to use this step, right? So first and foremost, marked as current limiting. So what we do in this case, it's sort of similar to that transformer example, right? We look up that let-through current. So we find a prospective fault current, those fault currents that ideally we're wanting to raise our branch to, and we look up how much of that current gets let through that breaker during that short circuit condition. And then, right, we will compare that, and the short circuit current rating, if the let-through current is less than a component short circuit current rating, we can raise the short circuit current rating of that component, but very, very importantly, we cannot use that let-through current to raise a branch interrupting rating. Right, so the branch interrupting rating stays the same regardless of that let-through current. So the short circuit current rating is going to be equal to either the lowest interrupting rating or that component SCCR. So let's do some examples here. It's going to be a lot easier once we do some examples. So right, in this case, I have a current limiting circuit breaker. you can see this let-through chart on the right, right? So I've got this let-through chart. I'm going to say I'm going for 100 Ka. So 100 Ka, I go up to the let-through chart for this breaker, and I go over and I can see it lets through 40 Ka. Pretty decent reduction, right? Instead of seeing 100 Ka, everything downstream sees 40. Okay, I put a current limiting circuit breaker in my feeder, and then I'm going to my branch where I have a breaker with an interrupting rating of 14 Ka and a contactor with an SCCR of 22 Ka. Have I done any good in this situation, right? Did I raise any of my short circuit current ratings? And then the answer, of course, here is going to be no. No, my animation's not quite working right here, but in this case, the short circuit current rating here is going to be 14 Ka still, right? So, a lot of people think, oh, if I put a really current limiting device in my main of my control panel, I'm good, right? Because everything downstream is going to be protected. And it's actually probably the most important thing is we want to make sure that that let through is actually less than those values downstream, right? So we want to make sure it's less than the values downstream. And my other scenarios, oh, there we go. I've got, right, 14 Ka. And in this case, right, now I have taken my 14 Ka rated device, right, that 14 Ka breaker, and I've moved it over, right? So now I've got a 65 Ka breaker in scenario 2, and the SCCR of my downstream device is 50 Ka, right? So now in this case, right, 40, that's less than 65, it's less than 50, so I can raise the SCCR of this, right? And if I can raise the SCCR of it, what can I raise it to? I can raise it to 65 Ka. So this is a very, very important example because it shows you how that let-through, using that let-through, I'm able to increase the short circuit current rating of that contactor, but I'm not able to increase the interrupting rating of the breaker. So if I wanted to get this up all the way to 100 Ka, I would have to have a 100 Ka interrupting rating device in my branch, right? So then I am able to have it be all the way up, and I don't know what is, but once I had that 100 Ka breaker in my feeder, there we go. Oh, then I'm able to raise it up to 100 Ka. So that's how to work with breaker. Remember that the let-through, right, the let-through using a current limiting main doesn't guarantee that it's going to increase the short circuit current rating of your whole panel, right? You have to verify that that let-through is lower than the ratings of what's downstream. And then you have to make sure you cannot use it to raise interrupting rating. Very, very similar when we use a current limiting fuse in the feeder. So it's the same idea. We're going to look at let-through current, and we're going to look at those ratings downstream. You still cannot use a fuse to increase interrupting rating, right? You can only use it to raise short circuit current rating. One sort of quirky thing important to know about using a current limiting fuse in your feeder is that you don't, unlike a circuit breaker, in a circuit breaker, we went to the manufacturer's table for current limitation. We went to the manufacturer's table, we looked up available fault current and let through, and that's what we used. That's not what we do with fuses. With fuses, we have to use UL 508A table SB 4.2 to determine what the let through is. Other thing about table SB 4.2, you can see here I've got fuse type, and I have 3 columns. I have a column that is like a 50 Ka column, a 100 Ka column, and a 200 Ka column. So I don't get to pick, I can't use 65 Ka here, right? I look up what the let-through is at only these specific let-through values. So if I looked at an example here, right, so let's use a 30 amp fuse. So a 30 amp fuse, I can see a 50 Ka, it'll let through 6 of peak let through. That's the other very important thing here is whenever we're looking at this chart, we're looking at that IP, that's peak let through, times 10 to the third, the Ka value. We don't use the I squared T value really in UL. It's not used for short circuit current rating in a UL 508A panel. We're always going to use the peak let through value. So 30 amp fuse, right at 50 K, it lets through 6. At 100 Ka, it lets through 7.5 Ka, right? And it makes sense, right? When it sees a higher available short circuit, it's going to let through more. 200, it lets through 12. So the important thing to know about these columns, right, is whichever column I pick, right, whether it's the 50 Ka, the 100 Ka, the 200 Ka, whichever column I pick, and the peak let through value there, that is the value to which I can raise the short circuit current rating of my circuit, right? So that's what I can raise the short circuit current rating to. I don't get to automatically make it equal to the interrupting rating of the fuse. I make it equal to whichever column I looked up that value at. So we're, again, going to go ahead and do an example here. In this case, I'm using a 200 amp cube fuse in my feeder. My 200 amp cube fuse, right, and we're looking, very importantly, we're looking at that 100 Ka column. So at 100 Ka available, the peak let through of this fuse is 20 Ka. So I'm going to use that value, 20 Ka as my let through value. So again, scenario 1. Current limiting fuse in my feeder, let through 20 Ka, downstream rating 14 Ka, 22 Ka. Have I done myself any good, right? I put a super current limiting fuse in my main, right? I have a high short circuit current rating in my panel now, right? No, I do not, right? I have a 14 Ka branch here, right? So I still have to actually verify that my let through is less than my component ratings downstream. So I'll take this let through and I replace my 14 Ka interrupting rating, my really low rated, and it looks like I put some 200 Ka fuses in there. Now, is 20 less than 200? Yes. Is 20 less than 22? Yes. So I can raise the short circuit current rating of this branch, and what can I raise it to? I can raise it to 100 Ka, right? And why can I raise it to 100? Because that's what the 20 Ka let through was based on, right? That's the column from table SB 4.2 I was using. If for some reason I lived in a world where 100 Ka was not enough and I wanted to get it up to 200 Ka, then I would have to use the peak let through at 200 Ka. Peak let through, I put it in the bottom right hand side here. The peak let through at 200 Ka for this fuse is 30 Ka. So if I had a 30 Ka let through in this exact branch, it wouldn't do me any good, right? Because 30 Ka is going to be higher than 22. I'm not going to be able to raise it. The highest I can raise this branch to is 100 Ka. If I really, really needed to get to the 200 Ka, though, I would have to replace that downstream component with something that had an SCCR of higher than that 30 Ka. You can see that in scenario 3 here, I have changed that let through to 30 Ka. And once I use the 30 Ka let through, now I can go all the way up to a 200 Ka short circuit current rating branch. So, right, we can only raise it up to the column. And I didn't do an example here, but the same remains as with we did the current limiting breaker. It's just very important to remember that you cannot use this let through to increase the interrupting rating of anything of any overcurrent protective device in your branch. Right, this only works to increase short circuit current rating of components in your branch. Really important. So here's some important rules, right, when you're applying these current limiting devices. So I'll say this, 10 times if I have to, but really, really important. It's a common misapplication is that current limiting breaker or current limiting fuse, it cannot be used to raise the interrupting rating of a downstream overcurrent protective device or the SCCR of a combination motor controller. So combination motor controllers are also sort of exempt from being able to have this current limiting device increase. A current limiting breaker or fuse cannot be used to raise the SCCR of a component in the feeder, right? So it's very important that we remember that this particular application, this is a current limiting device in my feeder, increasing the SCCR of the branch. Right, so it's not a feeder device helping a feeder. Similarly, number 3 here, right? It's not a branch device, right? A branch current limiting device raising branch, right? This only applies to a current limiting device in your feeder increasing your short circuit current rating in the branch. Really, really important we note that. So there we go. Whew, we are done with step 1 of determining SCCR. So determine the SCCR of each branch circuit. We went through part A, we went through part B. Good news, 2, 3, and 4 are a lot easier of steps to follow. So to determine the SCCR for each feeder component, right, that's generally just look up what devices in my feeder, those on the supply side of my branch, have a short circuit current rating. In this particular example panel, that's going to certainly include our power distribution block. And just one thing to note is that can be sort of forgotten is that in this case you can see there's fuses in a fusible disconnect switch. The fuses are going to have an interrupting rating, but that disconnect switch will have a short circuit current rating, right? And I'm pretty sure that anything that fuses are in it's gonna have a short circuit current rating of probably 200 kA. It's just something that you want to include, right? Whatever the fuses are in, they have a short circuit current rating as well. And then step 3 is to identify the interrupting rating for every overcurrent protective device. We've probably at this point already identified those in my branches. Again, we include those. We include interrupting rating in my feeder, and then another important thing not to forget is whatever the primary protection for my control circuit is. Again, this example, we're showing a transformer, but this could be a 3-phase power supply as well, right? So it could be whatever is protecting your power supply, but that primary protection going to your control circuit, that still counts towards your short circuit current rating. And then, of course, pick the lowest values for steps 1 through 3, and that is the short circuit current rating of your panel. Really quickly, I promised I would show you this, and I am following through on that promise, right, is that that current limiting device supplied in the field. So this generally applies to, and this is becoming more and more common, a panel where you are being fed from something like a safety switch, right, that has current limiting fuses in it. There are a lot of reasons to do this. One, it reduces the size of your enclosure if your main is outside of it. But a lot of people do it for sort of arc flash and shock reasons, right, because as soon as you turn off that main, if that main is outside of the panel, then you have no live anything when you open the door. So a lot of people for that arc flash shock reasons really, really like to use this. And it's totally allowed, and we probably want to be able to use that upstream fuse to help us increase our SCCR when we can, and that's fine. UL 508A allows us to do that with a specific labeling requirement, right? So you're going to have to mark the SCCR and list the type and size of that feeder protection. So you'd say the SCCR is 100 Ka when fed by a 200 amp Class J fuse. Otherwise 5 Ka, otherwise 10 Ka, whatever it would be, you would include that as well. So you can absolutely design your panels this way, where you have the upstream disconnect outside of the panel to help you with arc flash and shock hazards, and still take advantage of the current limiting device in there to help you achieve a high short circuit current rating, provided you label it this way. So with that, we are going to go ahead and do one practice problem today on short circuit current rating, and then if you come back and watch part 2, we'll go through a whole lot more of them. So here is my sample panel for this example. You can see A is my main circuit breaker, feeder breaker. It's a 100 amp circuit breaker with an interrupting rating of 35 Ka. It's feeding a power distribution block that has a default short circuit current rating of 10 Ka or a short circuit current rating of 14 Ka with a 125 amp breaker. It's feeding, we've got a branch CD is a 15 amp class DC fuses and holder with an interrupting rating of 200 Ka, and the SCCR of the holder is 200 Ka. It feeds a 10 horsepower drive with default SCCR of 5 Ka or a short circuit current rating of 100 Ka with a 15 amp class DC fuse. We've got branch EF, which is a 15 amp circuit breaker with an interrupting rating of 22 Ka that feeds a 20 amp contactor with a default short circuit current rating of 5 Ka, or an SCCR of 22 Ka with a 30 amp or less breaker. And then finally, the primary protection for my control power transformer is a 2-pole 6 amp miniature circuit breaker with an interrupting rating of 10 Ka. So we're going to go ahead and go through this and figure out what the short circuit current rating of this panel is. So I'm going to start, right, with step one. What was step one of calculating my short circuit current rating? It was to determine the short circuit current rating of my branches, right? So let's start with branch CD, right? And that is the easy. So C was easy, right? It's just going to be 200 Ka, right? 200 Ka with the fuse, interrupting rating, and the holder. That's feeding this 10 horsepower drive. Default 5 Ka or 100 Ka with a 15 amp class DC fuse. Am I feeding it with a 15 amp class DC fuse? Yes, I am. Therefore, short circuit current rating of that drive is 100 Ka. And the short circuit current rating of that branch is 100 Ka. Now, and I would also normally go, right, step 1B is let me see if there's a current limiting device in my feeder that can help me. This says nothing about my 100 amp circuit breaker. My feeder breaker doesn't say anything about it being current limiting. So I'm going to skip step 1B, right? I just do that 1A and I'm done. I will do the same here with branch EF, right? My breaker has that interrupting rating of 22. And my contactor, right, it's 5 Ka default or it's 22 Ka with a 30 amp or less breaker. I'm using a 15 amp breaker. That is 30 amps or less. So the short circuit current rating of that contactor, 22 Ka. Short circuit current rating of that branch, 22 Ka. And again, I skipped that step 1B because I have no current limiting device in my feeder to help me raise short circuit current rating. So that's it for my branches, right? I've calculated all of my short circuit current ratings for my branches, so I can move to determining the short circuit current ratings for anything in my feeder, right? That was step 2. So what in my feeder has a short circuit current rating? Only this power distribution block, right? So the power distribution block has a short circuit current rating of 10 Ka or a 14 Ka rating with a 125 amp breaker. I'm feeding it with a 100 amp breaker. So is it going to be 10 Ka or is it going to be 14 Ka? It's going to be 14 Ka, and that's because if we remember, I'm always permitted to use a smaller amp rated device than what is listed, right? That 125, that is a maximum size of that breaker. So I am using a 100 amp breaker, so I can still go ahead and use that 14 Ka. And then my 100 amp circuit breaker has a 35 Ka, right? We're in step 3, which is identify my interrupting ratings. So I mark my main circuit breaker, interrupting rating of 35 Ka, and then what I want to make sure I don't forget about is that primary protection for my control power transformer. That miniature circuit breaker has a 10 Ka rating. So that's right. We've accomplished steps 1 through 3. So we get to do everybody's favorite step, step 4, right? The panel SCCR is the lowest value from steps 1 through 3. As far as I can tell, the lowest value on this page is 10 Ka. So nice little 10 Ka rated panel here. That's the lowest value. Ideally we like to have panels with a higher short circuit current rating than 10 Ka. So for that reason, we have a part 2. So that concludes all of our examples here for part 1 of determining the short circuit current rating of a panel. But we'll go through more examples, different strategies to help you increase the short circuit current rating, so we can go sort of component by component and see, what's our best solutions here to increase the short circuit current rating. And then we'll also cover a couple common misapplications that I see out there in applying UL 508A. So we'll make sure we get all of that. And with that, I will hand it back over to Jill.
Thank you, Christy. That is going to conclude today's webcast. On behalf of Bussmann, thank you so much for your time. Please join us in 2 weeks for part 2 of this session. As she mentioned, she'll be A lot of it will be spent on ways to increase SCCR, and also stay tuned to Bussmann University for announcements on additional topics. You can also watch any previous webcasts on demand. Have a wonderful rest of your day.